Hello, good afternoon, everyone. I hope this is a post-lunch session and everyone is very eager to hear from the experts for geological and geophysical characterization. We are all ready, okay? Thank you, thank you. I can see very enthusiastic team here who is listening to the enthusiastic speakers. Okay, so I will introduce the speakers first. Let me introduce first myself. I'm Sanjay Thakkar. I come from downstream background, right from oil refining to petrochemicals to all the downstream value chain. We have an expert panel who will be talking about all the upstream things.
Good afternoon, ladies and gentlemen. We welcome you to third edition of IEW 2025. The show timings for today are from 10 a.m. to 6 p.m. Please take care of your belongings. Thank you.
Sorry for the interruption. Yeah, I'm business director with Emerson, and I take care of project pursuits, refining, petrochemical, fertilizer, anything and everything, including ONGC is my customer. Okay, so with that background, we are starting with Ansul Kesharwani, who is a senior geologist in Oil and Natural Gas Corporation. Currently, he is with the subsurface team for Mehsana asset. He is experienced, I will say, the expert in drilling horizontal and high angle wells, an expert in thermal and chemical enhanced oil recovery techniques. We'll start with Anshul. Yeah, you start. Is that fine? Thank you.
Thank you, Thakkar sir. Good afternoon, everyone. It's a privilege to be here at India Energy Week 2025, where we gather to share insights, developments, and exchange ideas which will shape the future of energy transition, energy sustainability, and energy dynamics. I'm excited to present my findings on Mesozoic exploration of Kutch Onland Basin, which plays an enormous potential in hydrocarbon potential. The Kutch Basin, with its well-preserved Mesozoic stratigraphy, is of a unique window in a geological past with its distinct depositional environment and tectonic implications. Understanding the basin's petroleum systems such as source, reservoir, carrier are important in terms of petroleum system establishment. My presentation will take you to the geological fieldwork which we have done few years back and observations of major structural and tectonic elements and how they will be helpful in establishing a petroleum system. Through this, I will discuss how the field geology provides fundamental knowledge about the outcrops, what are the different depositional environments, what are the major structures, minor structures, what are the tectonic history, and how they will deposit different type of petroleum system elements. So now, geologically, Kutch is renowned for its distinct Mesozoic rock formations such as Jhurio, Jhumara, Jhuran, and Bhuj, which was earlier classified as Pachtam, Chari, Katrol, and Umia Bhuj formations. It is the basin which is situated on the western margin and pericrotonic rift basin. We have done field work in December 2021, and this presentation highlights the significance of outcrop analysis and structural geology in evaluating depositional history and landforms and their role in hydrocarbon potential. This is the geological map of Kutch Basin showing the Mesozoic and Cenozoic outcrops. There are few Mesozoic, we have visited multiple Mesozoic and Cenozoic outcrops, but majority of my presentation is now considered towards the Mesozoic outcrop because we have established the Cenozoic petroleum system in fewer parts of offshore area and we don't have substantial amount of discovery in the Kutch Onland area. So we have mainly, our presentation is mainly confined to the Mesozoic potential of Kutch Basin. Talking about the major tectonic elements of the Kutch Basin, we have five major faults in the Kutch Basin: Nagar-Parker Fault, Iceland Belt Fault, South Wagad Fault, Kutch Mainland Fault, and North Kathiawar Fault. These faults are important because these faults created the accommodation space and tectonic movements which has subsequently deposited the sediments into the basin. Following that, we have five major uplifts: Nagar-Parker uplift, Iceland Belt Uplift, Wagad Uplift, Kutch Mainland Uplift and Kathiawad Uplift. These uplifts are important because of reservoir distribution pattern in the Kutch Mainland area. Pattam, Chari, Khadir, Bela and Chorar Island are the main island in the Kutch area, which is also indicating towards the basinal tectonic history. Now, this is our first outcrop showing the tectonic evolution of the Kutch basin. This outcrop from the Jhuran formation, very near to Bhuj district. As we can see, the normal fault is very clearly visible in this slide, and we have some parallel normal fault as well. So, these normal fault clearly indicating towards the extensional tectonic regime of the Kutch basin. Since Kutch is a peritectonic rift basin which was formed during the northward rift of the Indian plate. So, normal fault is clearly visible in this slide, and some parallel normal fault are also visible. On the other side, we have baking effect due to this dolerite dike. So, dolerite dike baking effect is important because some earlier studies also suggested that due to Deccan troughs, some amount of source rock thermally matured in the Kutch basin. So, baking effect is also important. On the other side, we have set of conjugate faulting, and highly smearing of layer is clearly visible in this slide. This is the Mesozoic stratigraphy of the Kutch basin starting from the Sinitic basement. We have Jhurio, Jhumara, Jhuran and Bhuj formation, and further which is overlain by the Deccan troughs. The Mesozoic package of Kutch have late Triassic continental deposit which was deposited during the basin formation, followed by late Jurassic marine deposited that was deposited during the marine transgression, and finally we have fluvio-deltic deposits. Majority of the Bhuj sandstone is considered in the fluvio-deltic regime. So, Bhuj sandstone is one of the major promising source for the source rock in the Kutch basin. And also from west to east, we have significantly on the western side we have thicker sediments, on the eastern side we have thinner sediments. Majority of the still exploratory drilling has been done in the northern part of the Kutch basin, either some eastern part of the Kutch basin. Currently, we have one well under drilling in the Kutch basin, which is drilling for one exploratory well, which is drilling for the establishing the stratigraphy in the Kutch basin. I will show in the further slides. So, this was the methodology or field work. Our field work was designed to provide the comprehensive understanding of the any outcrops. So, first we have done the traverse mapping and the contact mapping in the Kutch area. Followed by we have reached to the each outcrop. Each outcrop was detailed investigation was done on each outcrop, such as what are the major lithology, shale, sandstone or the limestone. Then we have observed major and minor structures in those faults, major minor structures such as any kind of soft sediment deformation structure present. Then followed by we have considered any tectonic implications, either any tectonic movement is visible in that outcrop. Then finally we have considered the paleo-environmental and paleo-geographical reconstruction. That is important because in the Kutch offshore area, we have established Mesozoic plays and fewer discoveries in the offshore area, but we don't have significant discovery as of now in the Kutch onland area. So, paleo-environmental and paleo-geographical construction will help in the establishing the outcrop surface to subsurface ties in the Kutch onland area. This is the location map showing the day-wise traverse. We have traversed various outcrops on these 4 days, and different outcrops were encountered in these 4 days. I will tell each in detail. So, this is the outcrop from the day 1 and day 2. In the outcrop A, we have trough cross bedding is present in the outcrop 1, and in the outcrop B, we have herringbone cross stratification. Herringbone is the fish bone. Herringbone is indicating the herringbone is indicating the bimodal paleo current direction. In the trough cross bedding, we have identified there are dynamic condition at the time of the deposition, so trough cross bedding has been formed. In the image C, we have observed breakup unconformity, which is transferring the active margin to the passive margin. From the active margin, we have the massive sandstone, and in the passive margin where the transgression was happened, we have observed the sandstone and some limestone with the bioturbation structures. In the image D, we have observed on the top of the middle Jurassic Jhumara half dome. So, highly fractured sandstone and cooling fractures has been observed in this outcrop. In the image E, we have dome having the highly curved structure. These all structures are important because fault entrapment is very important and fault closures are very important in terms of hydrocarbon exploration and establishing a petroleum system. In image we have the Rudramata river section. We have shale in this outcrop, and sequence stratigraphic framework also been established based on the downlefts of the sandstone. These are the few more outcrops from the day 3 and D4. We have dolerite dike. We have observed dolerite dike very near to Bhuj. Recently, I just want to let you to know, we have drilling one well and we have encountered around 150 meter sill in the current drilling exploratory well. So that sill also of dolerite. So we have observed same dolerite outcrop very near to Bhuj. In the image C, we have fracturing of dolerite dike and columnar joints are clearly visible in this slide. These are the image is very important in terms of the Kutch mainland area, because our currently developed the one exploratory well which is under drilling is very near to this outcrop, around 20 kilometers away from this outcrop. Or this is the sandstone, massive sandstone, and shelled out face is also present here. Image F is also important. We have observed clear contact between the highly weathered Deccan traps and the Bhuj sandstone. So it is a clear-cut stratigraphic pinch-out situation in the Kutch area, which further formed the stratigraphic pinch-outs and traps in the Kutch area. These are few more outcrops. These are the shelled out faces on the Bhuj-Mandvi highway, and some trough cross stratification in massive sandstone was also present on the Bhuj-Mandvi highway. And majority of the exploratory drilling is currently focused on the Bhuj-Mandvi highway and near around area. So we after this one exploratory well, we have one more well in the northern part to establish hydrocarbon potential. So these are the insights from the prevailing exploratory efforts. We have 3 exploratory wells, L1, S1, SN1 has been drilled, and different sedimentary sequence has been observed in this area. In terms of reservoir quality, 5 wells shall be drilled in the Kutch mainland area, which are mainly on the eastern side. So these have late Jurassic to early Cretaceous Juran and Bush formation with porosity and permeability ranging up to the 34%. The tectonic style and basin characterized by the east-west ridges also having some hydrocarbon potential. These are the few discussion parts. Since I have already told, the similar rift basins in the adjacent Indian subcontinent has been established Mesozoic place. In the South Badin and the South Indus basin in the Pakistan, Shahgarh, Jaisalmer, Shahgarh basin and Jaisalmer basin in Rajasthan, and also established the Mesozoic place. In the Kutch Saurashtra offshore area, we have Mesozoic place. In some Cenozoic formations also have hydrocarbon potential. So regional evaluation suggests that there are some potential in the Kutch on mainland area, and there is hydropetroleum system present, and all the elements of the petroleum system are present in the Kutch mainland area. So there is possibility of hydrocarbon in the Kutch mainland area in the all 4 formations, Bhuj, Jhurio, Jhumara and Jhuran, all 4 formations. This is the conclusive slide. So as I already told, key source, reservoir and seal, all the rocks, elements of the petroleum system are majority of the petroleum system are present. Also we have some Deccan trap in the Kutch area which can be thermally matured the oil. Also middle Jurassic Jhumara half dome suggests the thermal maturation reached during the Mesozoic era. So these are the major conclusions that we have oil in Kutch basin. Still we are trying to find, and definitely we will succeed one day. Thank you, sir, for your patient hearing. Thank you. Any questions, please?
The questions we can take later.
Okay. Thank you. Thank you, sir.
Thank you, Anshul. Now I will invite Dr. Shrey Badani, who is a geohazard specialist with BP. Currently he is with BP TSI subsurface. Earlier he has worked with Tenon Energy UK, where shallow geohazard assessment he has carried out across UK. He is expert in 2D, 3D UHR seismic interpretation for ground model development. Welcome, Dr. Shrey.
Thank you very much. So I will talk about some of the largest submarine landslides in the Mediterranean. This is the work that I did during my PhD several years ago. So I will give you a small disclaimer from my legal team that all views presented here are mine. And a quick outline of the presentation is, first of all, I will talk about why do we study landslides, why they are important. Then I will introduce you to the Mediterranean, and then I will tell you about the geological history, but very quickly. And then some of the mass transport deposits, then I will tell you their ages and some of the geotechnical analysis we did on the sediment course from the Mediterranean, and then I will conclude. Why it is important to study submarine landslides? I mean, they shape world's continental margin by redistributing sediments from the shelf to the lower slope, or from the lower slope to the abyssal plain, and they pose a geological hazard to the offshore infrastructure, such as we have seen in 1929 when some of the landslides broke telegraph cables in east of Canada, and several other examples such as in Algeria, Taiwan. And most importantly, they are dangerous to human settlements. They can trigger tsunamis, and we have seen some examples, for example, in 1998 in Papua New Guinea, and very recently in 2018 in Indonesia, in Palu, which killed a few people. Let's talk about the Mediterranean. It's a very busy area. As you can see, there are a lot of cities like Barcelona where you go on holidays. There are a lot of submarine cables that I'm showing in the dashed lines that are crossing the Mediterranean and the global ocean. And at the same time, my colleagues, Urgeles and Kamerling, they mapped about 700 failure scars and about 900 mass transport deposits associated to these scars. And they are all situated in the Mediterranean. And I mean, these ones are highlighted in this light green color that you can see, these weird looking polygons. And in the middle of the Mediterranean, you see these three brown color polygons. These are the large mass transport deposits that I have studied. And these are called as the Rhone Western Mass Transport Deposit, Rhone Eastern Mass Transport Deposit, and the giant one in the middle is Balearic Abyssal Plain megaturbidite. And when it comes to the sizes, they have a surface, the northern ones have a surface area more than 6,500 square kilometers, and a volume associated more than 150 cubic kilometers. And the Balearic Abyssal Plain megaturbidite, it has a surface area of 77,000 square kilometers, and a volume associated is 600 cubic kilometers. And just to give you a context, this represents half a meter of sediment covered all over Delhi. And so a little bit about the Gulf of Lyon, which is a passive margin situated towards the east, southeast of France and east of Spain. It has a wide continental shelf of about 250 kilometers and about 70 kilometers wide. And there are about 15 submarine canyons that cross the Mediterranean shelf slope, and the major one being the Petit Rhône Canyon that I'm highlighting in the yellow color that you can see. So what happened during the last glacial maximum about 20,000 years ago? The sea level was about 120 meters below present day sea level, and the entire shelf of Gulf of Lyon was subaerially exposed. And during this time, and please bear with me if I can show something. The Rhone River, which drains its sediments somewhere around here, it was draining its sediments right at the head of the canyon about here. And so it has been depositing all its turbiditic sediments right at the flank, right at the shelf edge. And with the sea level rise after the Holocene, the whole Rhone delta has shifted landwards, and today we receive sediment of hemipelagic to pelagic in nature. And this has not been happening only since the last glacial maximum. We have been seeing the cyclicity of high stand, low stand since the onset of the Milankovitch cyclicity, which is 100,000 year cyclicity in the global ocean. And what happens during these climatic cycles is that during the highest end, we have a sedimentation rate of 5 to 10 centimeters per thousand years. And we receive sediment, as I told you, pelagic, hemipelagic, which is abundant in forams and other microfossils, and which is represented by these high amplitude seismic phases in our seismic data. While on the other hand, during the low stand, the sedimentation rate increases significantly to 1 to 2 meters per thousand years, and the amplitudes of these sediments are represented by these weak amplitudes in our seismic data. So let's go. There is another structural heritage in the Mediterranean, which is related to the Messinian salinity crisis. What happened during the Messinian time, about 5 million years ago, the Mediterranean closed, and the whole water of Mediterranean evaporated, and which left a thick pile of salt in the whole basin. And salt is mobile with the overburden of the sediment. The whole slope of Gulf of Lyon has been gliding downwards, and which are represented by these steeply dipping listric fault. And with the pressure, the salt pops up in the deep basin, which are represented by these funny looking diapirs in the bathymetry. Let's talk about the mass transport deposit now. The source of the eastern mass transport deposit is called as the Eastern Rhone interflow slide, and where we observe at least 5 head wall scarps associated with it. And there are 2 active fault grabens that are cross-cutting at the toe of the landslide. Looking at the internal architecture of the subsurface here, there are this line crosses towards the east of the slide here, and we have penetrated the head wall scarp 2, 3, and 4, and then you come to the fault graben here. And so I'm not going to go too much into detail. I will just ask you to focus to this cartoon in the middle. So this is my slope here before the failure took place. The fault existed at that time, and about 21,000 years ago, the fault reactivated, leaving this exposed strata at the bottom, and which triggered the landslide at the toe. And with time, the failure propagated towards the shelf in a retrogressive style. And so we wanted to see when exactly the failures took place, and what is the ages of these deposits. So we did some radiocarbon dating and oxygen isotope dating. And so the ages of the deposits right on top of the landslide deposits, I got in the 3 mass transport deposits. These are the eastern, western mass transport deposit and the BAP megaturbidite, and I get an age of between 19.5 thousand to 21.7 thousand, and which falls right at the peak of the last glacial maximum. So there is definitely some common trigger behind these landslides. And talking about the basal surfaces when they were deposited, so we got lucky, and 2 of our sediment cores, they penetrated these basal surfaces. And let me show you, this is a very complicated slide, but I'm not going to talk too much about it. So just going to say that the basal surfaces 2, which is BS1 and BS2, were deposited during the marine isotopic stage 5 and 7, which is an interglacial period. So we also wanted to know what the sediment looked like. So and again, because there is the failure taking place all over the Mediterranean over these high amplitude reflections, so it becomes even more apparent that we need to know about these sediments. So in the next slide, we did some grain size analysis, and when you look at the basal surface around here, this is just an example of one of the sediment cores, and we see a segregation of a finer grained material, which is clay in fraction, just at the basal surface. Whereas when you go above the basal surface, there is distribution of sediment from clay to fine coarse silt. And not even this, I mean, you can already see that this is the basal surface here. This is a 20 centimeter interval of my core, and then these are the turbidites that are deposited. So there is definitely a lithological contrast between the sediment in the Mediterranean. So we wanted to know a bit more about them, so we did some geotechnical analysis, a very simple test where you put the sediment within a cylinder and then you shear the sediment. And we also measure the displacement and the load that is being applied to the sediment at the same time. So another complicated slide, but I will just ask you to focus towards the colors, which is the green, blue, and red. So I'm showing the green are the turbidites here, then blue and red are the two basal surfaces. As you can see, in the turbidites, we have, when the sediment is shearing, when you apply the load, after shearing, the sediment strength remains more or less the same, while in case of the basal surfaces, you see the shear strength becomes high, and then after the sediment is sheared, then the shear strength drops down. And there are two types of behaviors that are associated with it. In case of the basal surfaces, we have a strain softening, while in case of the turbidites, we have strain hardening. And this is a very predominant failure or preconditioning factor to trigger the failures in the Mediterranean. I mean, on top of that, we did some geochemical analysis on these on the sediment cores, and we found out that just at the basal surfaces, we have higher potassium content, and potassium is a very good geochemical proxy for illite, which is a clay mineral and has flaky texture, so they are more prone to, so the basal surfaces are more prone to failure. And with this, I would like to conclude is that we observed multiple head wall scarps in the source area of the landslide, which are aligned in a staircase style. And each basal surface of these failures are associated with high amplitude reflections, which are associated with the interglacial sediment. And delta 018 results again saying that these high amplitude reflections were deposited during the interglacial period, and we observed some strain softening within these basal surfaces, which can explain the bedding parallel failure mechanism. And then radio carbon dating puts these failure to the last glacial maximum, which can tell us about the preconditioning and trigger mechanism. For example, very high sedimentation rates, excess pore pressure, and etc. And this is my last slide. I would like to acknowledge the European Union for the funding as a Marie Curie grant, and I'm also highlighting the institutes that were involved during this research. And thank you very much.
Thank you, Dr. Shrey, for sharing your studies about seafloor instabilities. Now I invite Dr. Vishal Raju Ahuja, who is a researcher with Shell India Markets Private Limited. He is a researcher in Computation Science Department at Shell Technology Center, Pune. And he will be talking about boosting accuracy of petrophysical characterization with micro-CT scanning and AI, a very interesting topic. Thank you, Dr. Vishal. Now you can take the stage.
Very good afternoon, everyone. Am I audible?
Yes.
Okay. Thank you very much, Mr. Thakkar, for that very kind introduction. As he mentioned, I'm a researcher in the Computational Science Department at the Shell Technology Center, Bangalore. And today I'm going to be talking about boosting accuracy of petrophysical characterization with micro-CT scanning and AI. As you can see, it's a very diverse, multidisciplinary topic involving petrophysics on the one hand, micro-CT scanning in the laboratories, and AI-based computations. So what I will do is I will explain the topic at a very high level with a lot of schematic diagrams and pictures so that it's very easy to understand for an audience as diverse as this. So without further ado, let me start the presentation. So before I start, I must show you this mandatory disclaimer slide from my company. Don't worry, you don't have to read the whole text right now. I will summarize it by saying, no matter how much you like my presentation, please don't make any investment decisions based on my talk. Yeah, that's about it. So brief bio about myself. So as you can see, I have a bachelor's and a master's degree in chemical engineering and a PhD in computational physics. So the reason I'm trying to tell you this so that you understand where I'm coming from. Yeah, so I come from a very hardcore chemical engineering and physics background, and I'm now trying to see where we can apply the latest technologies like AI to the field of sciences and how we can improve the accuracy as well as boost the performance of some of the traditional workflows. Yeah, so that's my area of interest. And the areas that I'm applying this to is hydrocarbon recovery, carbon capture and storage, and lately subsurface storage of hydrogen. So please follow me on Google Scholar and you will see some of the latest papers that I have in this domain. So coming to the topic, yeah, boosting accuracy of the digital rock workflow with AI. So let me start by first motivating why we want to do this, right? So if you think about the conventional way of how you would characterize, the rock samples petrophysically, you would do a regular and a special core analysis of the sample, right? So what it means is you take these cores, which you see on the extreme left of the slide, from the reservoir, and what you would do is actually experimentally try to determine the porosity, permeability, relative permeability, and such other properties, right? Now the problem with the experimental workflow is it's a very time consuming workflow, right from the initial stages of cleaning the sample, aging the sample, and finally getting to relative permeability can actually take you months of time, right? So what we are trying to do with the digital workflow is trying to accelerate this decision making. Can you get a faster estimate of the porosity, permeability, and relative permeability without having to spend months of effort for getting those properties? And so what we have here is the digital version of the SCAL workflow that you would usually do in experimental lab facility. So you start with the sample preparation. Here you basically try to first scan the whole sample with a CT scanner and try to identify the various facies that you have inside the sample. Once you have done that, then you can basically drill out mini plugs from each of these facies and characterize them with the help of micro CT scanning. Now why micro CT scanning? Because you will observe that the pore throats that you have in these rocks are in the micron scale, right? And hence you need to actually look at them from a micrometer scale. And hence we resolve them with a micrometer resolution using a micro CT scanner. Followed by that, we have the image reconstruction step. So you get all these projections from the micro CT scanner. It's very similar to how you undergo a CT scan at the hospitals. So you get all these projections, but instead of the detectors and the panels rotating around you, here the rock sample rotates. So you don't have to do that in the hospital setup and you don't rotate in the machine, but we have that liberty with the rock samples, of course. And you can also irradiate them at a very high radiation level, so you can actually get the structure at the microscopic level. And then we basically subject this to AI-based super resolution. And this is the novel block that I'm going to talk about in this presentation. But I'll come to that later. What we do after that is basically segment the sample into the various minerals that you have inside, as well as the pore structure. And after that, you subject them to computational physics-based simulations, where you can characterize the porosity, permeability, relative permeability, and we use lattice-Boltzmann method type of simulations to simulate these flow properties. So having understood the whole workflow, now I'll tell you why we insert this AI-based image super resolution inside this whole digital rock workflow. So what is super resolution, right? If you look at the picture of this baboon, I think everyone in the audience can say what's the difference between the left-hand side of the image and the right-hand side of the image, right? You see the left-hand side is having a much higher resolution as compared to the right-hand side. Now what that does is basically it provides you a much sharper image. Now why do we want sharper images of rocks? Because the simulators are only as good as the images that you provide to the simulators, right? So if you can improve the resolution, you can get a much better and more accurate results from the simulators. So basically, super resolution is a class of techniques to digitally enhance the resolution of the image for the same field of view, right? So the field of view you see in the left-hand side of the image and the right-hand side of the image is the same. It's just that one of them is a higher resolution, right? And why do you want to do it digitally, right? Because if you try to take a higher resolution image of the same field of view with a micro CT scanner, what you will observe is you will take a very large amount of time to get it at a very high resolution. So what we wanted to do was, can you take a quick scan at a lower resolution and then digitally super resolve the sample to get more or less the same accuracy, thereby accelerating the whole workflow. So the methodology that we use is AI-based deep learning. And what this deep learning network does is basically it trains on a number of different low resolution and high resolution image pairs and basically learns how to up resolve a low resolution image. So that's basically the idea behind it. Now the challenge, of course, is there is very little literature on this subject. As you can imagine, a lot of the super resolution methods in the field of deep learning and AI are applied to cats and dogs. So we wanted to see whether we can apply it to rock samples, right? And that's where actually we collaborated with the Indian Institute of Science, which has a great department for doing this kind of super resolution work. And they actually used to work in the medical field because there also you use a lot of CT scanners. And we said, okay, can we collaborate together and see that this academia industry story, can we make it successful? And can we try to see that we use your methods to actually apply it to rock samples, which is a completely different field where it has not been applied before. So without going into much details of this very busy schematic diagram, what I will try to say very simply is that these generative adversarial networks that are there for super resolution have mainly two parts. So as you can see, the top part is called the generator network, and the bottom part is called the discriminator network. Now what does the generator network do? It's like a very talented con man trying to basically mimic paintings of great artists, right? And the discriminator basically is like an inspector who's trying to see whether the image is real or not, right? So this is basically the whole idea behind a generative adversarial network, right? So the generator basically takes a low resolution image, converts it to a super resolution image, and the discriminator tries to distinguish whether it's a real high resolution image or it's a super resolution image generated by the generator. Right? So initially, as you can imagine, when the training starts, the generator is not very good at generating high resolution images, and the discriminator can easily point out, oh no, this is not a real high resolution image, this is a super resolved image generated by the generator. But as time proceeds and you train it with more and more samples, what starts to happen is the generator becomes so good that it starts to fool the discriminator, and at that point you know that your simulation is converged, because basically the discriminator cannot distinguish between a real high resolution image and a super resolved image generated by the generator. This is the basic principle behind the generative adversarial networks that are used in deep learning. Coming to our novel Siamese SR architecture, as we call it. So it stands for Siamese Super Resolution Architecture. Now why the word Siamese? It's just like the dictionary definition of Siamese, right? It's like twins inside the network, and basically you subject the network to two images. One is a high resolution image and one is a super resolved image, and you put them through the network, and these networks have the same set of weights, as we call them in deep learning, so same parameters and hyperparameters, and at the end you get two different vectors which basically tell you what are the features in each of these images. And at the end you can see how far these vectors are. If they are very close to each other, it means that you are actually having similar image. If they are very far from each other, means these images are very different from each other. So basically this was the innovation that we added on top of the discriminator that I showed you in the previous slide. So what you do is essentially, like I said, image 1 goes through the top part of the network, image 2 goes through the bottom part of the network. At the end you get these two feature vectors, and how do you decide whether they are close or not, right? You can simply take a dot product and you get a cosine distance between the two, right? And that's what we've tried to show on the right hand side. So if you have the images like we have in the top, which are very similar to each other, they will fall very close to each other in the embedding space, which is the feature vector space. And if the images are very different, they'll fall very far apart in the embedding space. And now I directly jump to the results, right? So basically what you see on the screen, on the left hand side is a low resolution image of a rock sample, and the right hand side is the higher resolution image of the rock sample that is generated by our Siamese SR network, right? So as hard as it is to believe, this is actually generated by the deep learning model, and it's not a real high resolution image. But as you can see, we go through the rock structure, right? So what we are showing you is actually a 3D structure. So you have a 2D image, and then over time you see as you go inside the depth of the structure, right? So you see all different kinds of microporosities in the left structure, in the left image, which are not very well captured. Whereas in the right one, you will start to notice that there are features which are very fine, and this will lead to a much better porosity and permeability estimate, as you can imagine. Now, how do you know whether you are good enough or not, right? That's the real problem. How do you know that you have actually reached the correct accuracy for the porosity and permeability, right? So what we did was we actually scanned the image at multiple different resolutions, and we tried to see at the highest resolution what is the porosity and permeability estimate that you get. So that is basically our benchmark to say this is what we want to achieve with the super resolution network, right? And you will be surprised to see that there's a huge difference between the high resolution and the low resolution porosity over here, right? So in the table you can see it's almost 13 pu for the high resolution image and only 10.3 pu with the low resolution image. So if you were to just take the low resolution estimate, you will be really off by 30% in your porosity, right? Which is very terrible. So what we did was, okay, we tried to compare a number of different literature methods which take the low resolution image to a higher resolution, which is the SR GAN, ESR GAN, EDSR, SPSR, and as you can see, they actually all over predict the porosity. Whereas our method actually comes pretty close to the high resolution image. While there is slight over prediction still involved, but it's much better than any of the conventional methods, and it actually comes pretty close to the high resolution method. Furthermore, more than the porosity, many of you might be interested in the curves that I have shown in the bottom left of the screen, right? So you have these mercury injection capillary pressure curves, which are typically used to analyze how the porosity varies inside the sample. And as you can see, the super resolution curve comes very close to the high resolution curve. And I've mentioned some of the parameters over there as well, like the porosity and then the shape factor. And you will see that they are very close actually to the high resolution value that you obtain. So this basically shows you that it's actually possible to super resolve these images digitally and get a very accurate estimate of porosity and permeability in a very short amount of time as compared to what you would do experimentally. Of course, having said that, it comes with its own set of challenges, right? So there are limitations to this approach as well. So one limitation which you can immediately recognize is it's only going to work for very homogeneous samples, right? So if you have very heterogeneous sandstones, and what I showed was sandstones earlier, as you can all see, and also for carbonate samples, right, where you have big vugs and then you have small microporosities, you have a very different length scale that is involved there. Having said that, we have also developed a similar workflow for that, and it's currently in the stage of manuscript preparation. So you will see that paper coming out soon as well. But since that is not out, I cannot talk about that work yet. But this one, if you want to learn more about this, we have our article which I referred in some of the previous slides in the IEEE Transactions on Image Processing Journal. And happy to take any questions that you will have outside as well as at the end of the session. So as you can imagine, this is a novel work, and it's just the beginning, right? So there's a lot of technology development further that is required in terms of elaborating the operating envelope for this technology. And also, you can imagine this is not only applicable to just hydrocarbon recovery, but it's also applicable to CCS, right? Because it's the same reservoir, you want to inject carbon instead of taking the carbon out, right? So also for other types of porous media like catalysts, direct air capture, as well as soil science, right? So many other applications also for this particular technology. And I wanted to emphasize on that because with a multidisciplinary audience, right, such as you can easily take innovations from one field and apply it to the other field. And that's where the real innovation is born. So very happy to collaborate with any of you if you find interest in your areas of application where you want to do this. And thank you very much for bearing with me.
Thank you, Dr. Vishal. It was really wonderful to see one more use case of AI, and with further scope of expanding the horizon. So very innovative. Okay, now I invite Divya Mishra, who is a senior geoscientist with geophysicist with ONGC. She will be talking about challenges and scope for deep water and ultra deep water hydrocarbon exploration beyond content ocean industry. She is skilled in geophysical, geological and geophysical data to identify hydrocarbon potential. So floor is open to you, Divya.
Thank you so much, sir. So without a further ado, as the topic says, challenges and scopes for deep water ultra deep water hydrocarbon exploration beyond continent ocean boundary. So going to talk about the challenges and scopes, I would like to speak a brief about the context of beyond continent ocean boundary, as well as what is the significance or the need of this study. So the point one, beyond continent ocean boundary. So sedimentary basins in which the hydrocarbon accumulates, resides, these are broadly categorized as active margin basins and passive margin setup basins. The scope of this study covers the passive margin setup basins and how this kind of passive margin setup basin evolves. For a general idea, when the hot rising magma comes to this, it exerts force on the continental crust, and wherever the weak zones are there, the breaking will happen. And in this way, the continental blocks will start to separate out, and at a certain point, when there will be a gap, or the thinning of the crust will be sufficient enough, the magma will start to come out, and in this way the formation of oceanic crust will start to take place. The oceanic material, the oceanic magma is coming at the oceanic ridge boundary, and it exerts the lateral force now, due to which the oceanic plate as well as the continental plate starts to drift apart. And as you can see right now, at the end of this rifting stage, when the drifting starts, there you can see the transition zone between the continental and the oceanic crust. It is the passive margin system. There is no kind of activity in terms of plume or magmatic activity, and that is why the term passive margin setup. And the configuration as a whole, if we are seeing, it is the self-slope abyssal plane system. So abyssal plane is the area where the oceanic crust regime can be found out. So this is the zone of interest which I am going to talk about. Point number 2 is, what is the significance of this study? So if few of the members who have been present before session, which was on the deep water, ultra deep water exploration, in that Rystad Energy has also given the reference that there is a huge potential which is yet to be tapped, which is sitting or residing in the deep water and ultra deep water regime. So globally this is true. So now this whole study or the presentation will follow the challenges and scope in terms of the petroleum system elements, which covers the challenges and scope for source rock presence and its maturity, as well as the major petroleum system element after the source rock presence, that is the entrapment condition. So since the oceanic crust still it is in the frontier stage, so globally we can find out some references in the context of ECMI basin. I will give a brief on that. So what are the challenges for the source rock presence over the oceanic crust? So to understand, let us have a brief on how the organic matter and hence ultimately the source rock deposition takes place. The mechanical mechanism takes place in 2 stages. One is the production of the organic matter, and another one is the preservation of it. So where the production of the organic matter will take place? The areas where the sufficient sunlight will be there and where the nutrients supply will be sufficient enough. How the nutrients will come into the system? There are 3 broad mechanisms: through upwelling, thermohaline circulation and runoff. This model represents the broader areas, what kind of organofasces can be deposited in different kind of environments. Fascies A and B, which are being deposited in the self-slope environment, these are the marine algae and bacteria. Fascies C, it is deposited, fascies C is the fresh algae which is deposited in the lacustrine environment, and fascies D, E, F, these are the terrestrial organic matters which used to be brought into the marine system through the river runoff. So in one terms, if we are seeing in the ultra deep water regime over the oceanic crust, the challenge is in terms of the nutrient supply and hence the production of the organic matter. So what is the scope? If we take a step back, we can see that the river runoff can be a way to bring the organic matter which is present at the terrestrial regime into the deep water system. There are 3 broader mechanisms: vertical settling, turbidity flow and debris flow, which bring the sediments into the deep water regime. It has been seen that the distal lobes which are getting deposited in the deep water, deep sea environment, these are not the influence of a single mechanism, but it is a hybrid of it. And it has been found out in there are 5 sequences: H1, H2, H3, H4 and H5. In the mid sequence H3, there is the deposition of organic matter possible with the mud accumulation. So this is all about the theory. So do we have any evidence for the presence of source rock over the oceanic crust? In that aspect, I would like to give a reference of the few wells which have been drilled under the deep sea drilling project over the oceanic crust in the Moroccan Atlantic offshore. So here it has been found out that torsion black shale, which is having the corrosion type 2 and 2S with good TOC content, is present. In the well DSDP 416, which has been directly drilled over the oceanic crust, in the Valanginian Hartruvian mud and siltstone, type 3 corrosion source rock has been found out, as well as the Albion Cenomanian shales has also shown the good source rock characteristic. In the context of ECMI, if we are trying to look, there are two wells which have been drilled, KG-A1 and A2, in the oceanic crust regime, and these wells have only penetrated the tertiary formations, which have reported that the type 3 kind of source rock is present with the poor to fair organic matter richness. Interestingly, there is another recent well which has been drilled in the Gulf of Guinea. This well, Jaka 1, it has reported the oil presence, and this oil has been associated with, correlated through geochemical analysis with the upper Cretaceous siliciclastic marine source rock. So there are the evidences for the presence of source rock over the oceanic crust. Now the next question comes, once the source rock is present, as we know that the thermal modeling, the heat flow analysis says that the major contributor for the heat flow, one is the mantle heat, another one is the radiogenic heat generated through the radioactive decay of the elements which are present in the crust. And as there is the continental crust and oceanic crust are having different compositions, oceanic crust is having basaltic with less radioactive elements, there is lack of that contribution of the source, heat source. That is why it has always been considered as the cooler regime, and it used to be overlooked, the petroleum system existence over the oceanic crust. So for that, David Rasman, what he has done a geological modeling for the thermal analysis. Thermal heat flow analysis has suggested that if there is the cutoff of 1% VRO we are taking, and the model he has made up for heat flow analysis is that he has taken the lithosphere thickness around 100 kilometer, and he has found out to attain the VRO of 1% over the oceanic crust, there is the need of 5 kilometer overburden thickness. In comparison to with the same kind of setup, this maturity can be attained over the continental crust with the 2.8 kilometer of the overburden thickness, and in the transition zone it is roughly around 4 kilometer. So he has proved that there is a contribution of the overburden thickness also, which is contributing for the source rock maturity. For the younger basin, for example for the Red Sea, it can be the sedimentary thickness required could be lesser than the 5 kilometer. It has been modeled as around 3.5 kilometer because of the heat flow, which is higher when the age of the basin is young, as we can see in the graph. So for the source rock which has been encountered in the Moroccan Atlantic offshore, it has been done few of the modelings which has suggested that if we are considering only the contribution of the overburden thickness for the same regime where the source rock is sitting at around 4 kilometer depth, it is falling in the early maturity stage, and which is validating what the Rasman et al. Has bring out through his model. But there is another scientist, what he has done, he has incorporated the contribution of the plume activity, which has the Canary hotspot activity which has been done over the Moroccan oceanic offshore in the late Cretaceous, and it has brought out in the model that the source rock of the torsion black shale, it can attain the source rock maturity with the transformation ratio of around 100% with the contribution of the heat flow which is being contributed through the plume activity. For the ECMI also this has been carried out, and it has been found out the Turonian late Cretaceous source rock are attaining the source rock maturity, which is sitting at around with the source rock which is having the overburden thickness of around 5 kilometer. This is the scenario, just to give a brief on how the global deep water discoveries in the past 40 years has been distributed for the passive margin setup, along with the discoveries or the exploration attempts which have been made over the oceanic crust, as has already been discussed in the Gulf of Guinea, Jaca 1 well, in the ECMI, and as well as the Moroccan Atlantic offshore. Along with, there are few wells, Lisa 1 everyone is quite well aware of, and the Raya 1 well, which was not a success but drilled in the vicinity of the oceanic crust. So with this, for the ECMI context, when we are talking about how to look for a global analogy, so we know that in the Atlantic offshore, southern Atlantic offshore, there most of the discoveries has been made based on the conjugate mirrors theory, which suggests that during the rifting, if the two set of blocks, they were at this sharing the similar stratigraphy, then there is the probability that if one of the system is having the petroleum system existence, similarly the other one, which is now separated apart, will be having the same. And on that very basis, Jubilee field discovery has led for the discovery in the Guyana Suriname. So for the Indian context, can we find out this kind of conjugate system? So we know that ECMI context, if you are seeing, it has been separated from the Antarctica, and since 1991 we are not having any kind of exploration activity in the Antarctica, well aware, because there is challenges of economical and ecological preservation, so we need it has been not done. So what are the other possibility to look for the analogy for the ECMI? So the study has been carried out by Wen. He has distributed the passive margin setup, passive margin of the global, which are present globally in the 7 categories, which are majorly categorized in the 4 parts: rift basin, faulted basin, depression basin, and reformed basin, based on the evolution of the basin. And further, based on the structural setup and the sedimentary fill, it has been subdivided into non-saline, saline faulted depression and faulted basins, and the reformed basin has been categorized as delta reformed and positive reformed. So if we look at the distribution of the different groups, sedimentary passive margin setup groups, the Tanzania and the ECMI basins are falling in the non-saline faulted setup of the basin. So from here, one analogy can be bring out. And if we are seeing the seismic as well as the geological configuration for the ECMI and Tanzania, it is showing that what kind of probable entrapment condition we can find out. It is the drape features which are present over the basement, the basinal floor fans, as well as the channel levee complex, which are being referred from the present context. Other than this, one interesting point I would like to mention, that this categorization should not be limited in this part, because oceanic crust is having a feature that most of the depositions are flat, parallel to the basement. If we look at the Moroccan offshore, though it is saline, but the saline bodies are limited to the transition zone. So if we look at the oceanic crust regime, it is also having the similar kind of configuration as the ECMI basin is having. So we can bring an analogy from the Moroccan Atlantic offshore also, in terms that it is having a kind of entrapment which is present due to collision of Africa as well as the Europe, which has generated the structural entrapment. So can we look for similar kind of entrapment over the ECMI East Coast basins, which may be associated with the Himalayan orogeny? These are few of the thoughts which may lead for the looking for a better entrapment conditions over the ECMI. So with this, the challenges are there, but we are having the scopes. Challenges for the presence of source rock, but deep water involvement over the ECMI presents the preservation scope of the organic matter over the oceanic crust. Maturity, we need to look for the other factors also which are contributing for the source rock maturity. For example, the overburden as well as the any kind of magmatic plume activity. And the exploration focus suggests that, as in the open ceremony today, Tanzania energy minister has mentioned that they are not having, they are having the conventional energy fuel in very kind of costly aspect. So here reverse is happening. ECMI can work as a reference, a global analog for the Tanzania basin, and for ECMI we can take a reference from the Moroccan Atlantic offshore for looking ahead any kind of good entrapment condition. Thank you so much.
Thank you, Divya. I think my friend Max may not allow me to have a few questions, but maybe one or two questions we can have. Yeah. Can we have a mic? Just maybe we'll be able to take only one question maybe. Just. I know we are short of time, so I will have one question only.
Hello. Hi, I'm Rahul. I'm from Shell. So I've done very interesting presentations, and especially an idea which intrigued me was a presentation from Vishal Rani. So very nice, I would say. So there was one question you talked about generative networks as well as the discriminator network, right? So what are the source materials for training your model for the discriminator network per se? If you are training them with respect to the results from the generative network, then anyhow it will always be 100% successful. So what is your source for training the model for discriminator network? That is.
Thanks very much for the comment as well as the question. So basically these generative adversarial networks, right, they come as a pair. So you have the generative part of the network and the adversarial part. Of course, if you take the standard super resolution generative adversarial network, those are basically pre-trained networks on a set of images, which basically usually is like the ImageNet database, which has a large number of images of all kinds of animals and dogs and cats, things like that. But what we did over here was, since we were interested in materials, right, rocks and things like that, so we actually trained it on a database which is called Materials in Context database, which has a number of different samples like wood, plastic, rocks, things like that. So we actually used a pre-trained network which had the relativistic discriminator pre-trained on the materials in context database, so that it's more applicable for our use case. And then on top of it, we added the Siamese discriminator, which actually provides an optimal level of denoising that you need for this. Because if you denoise it too much, right, then you get a very smoothed out image. And so this is the two innovations that we actually came up with. Thank you.
Thank you. I think with this we conclude the session. Thank you, Anshul. Thank you, Shrey, Dr. Vishal, and Divya. Thank you very much. It was all wonderful presentation. Thank you.